Okay, I think it's a good time to start. Good morning, good afternoon good evening to everyone. We normally do it in the afternoon, so depending on Anil's and Achusi's time, so we have scheduled this webinar in the evening. So again, good morning, good afternoon, good evening, everyone, depending on where you're joining. Thank you for taking time to attend. Today we have Anil Nair. I'm sure most of you know Anil is our what to say our speaker, and not is sitting in US, but still our speaker. It's our asset, our property. But we also have a new speaker today, Achusi Morimura. Sorry, Achusi, if I have pronounced properly. So there are two speakers today talking about diagnosing Oracle RAC performance issues, right? And if you don't know Anil, Anil is the product manager for Oracle Real Application Clusters. So he's ask anything on Oracle RAC, and Anil presented number of events, and especially in Sangam, he presented multiple times. So I'm sure, hope you know Anil. But I think I'd like to introduce Achusi. So he's the Oracle database performance specialist, right? So if you have any performance related questions, especially on the Oracle RAC, ASM, or clusterware or Exadata, this is the time you need to ask. So before handing over to the speakers, I want to cover a few housekeeping things. I know it's not a request, but tweet about this webinar. This is the only way you can connect with other attendees, also speakers, and make more virtual connections. I don't know how many months or how many years we are going to work like this, but at least we need to build the virtual network. Make AIOG webinar as a hashtag, so that that way you can find others also. So we also invite your comments and questions. Please look at the Q&A bottom of your screen. Please ask your questions for the speaker at any point of time by typing in the Q&A only. Don't do it in a chat window. And if you need any help or any support, or you want to say convey thanks to speakers, you can use the chat window. And also one more request, please prepare your questions properly before putting into Q&A section, right? So don't do like a single line. I understand the problem, like, for example, when you are talking through voice, it's easy to convey, but think before putting the question properly, right? We don't want to waste anybody's time here. And remember, knowledge is a power as long as it is shared. So do not say with you, share with others, right? Provide your feedback at the end of the session. I know we are not seeing much participation in the Survey Monkey, but again, we are requesting, we are all volunteers. We want to know we are doing the best or not for this community. So please spend 1 or 2 minutes, not beyond that, right? And submit your feedback. I'll come back to you, the feedback link and everything. So with that, very warm welcome, Anil and Achusi. And Anil had really good breakfast now. So let's go ahead and share your screen and present, Anil. Thanks.
Sure, go ahead. There you go. There you go. I hope everybody can see my screen, right?
Yep.
Perfect. Okay, welcome everybody. Thank you so much for attending or joining this call. I know it's a little bit interesting time, but as Sai said, we have a very interesting guest speaker along with me, and we need to make sure we can balance this time. But the good thing is, hey, it's going to be over just before IPL starts, so be good there. If you don't know me, I'm Anil Nair. I'm the Oracle RAC product manager, as Sai said. And the new thing is I'm also the ASM product manager. I'm trying to, call out like as a mission critical database technologies product manager. Anyway, it'll come soon. Why Oracle RAC performance issues? So in the past, we have talked about Oracle RAC, how it can scale, how it can do certain things. However, the truth remains, and we are very cognizant of it, that there are performance issues. There are certain customers who are running certain kinds of benchmarks or certain kinds of applications that says, okay, I don't see the benefits that Anil showed in his PowerPoint. So we really want to, reach out to you guys, see the issues, and also give you some tips and tricks on how to actually diagnose your performance issues. So when Sai approached me saying, Anil, can you do a session? I had like multiple choices, but this seems to be the most popular one. So hopefully you'll enjoy it. A lot of the things we're going to talk about today, some of them we have already have blogged about or talked about. So those are my LinkedIn and SlideShare locations. And as usual, if you have questions for me or at Sushi, if you have it right now, put it in the Q&A. But if it is after, feel free to reach out to me on Twitter. I'm fairly active, I would say, on Twitter, and do get back to people. So having said that, let's move on to the mystery speaker. So Atsushi, I couldn't find a good picture of you, so I think this is as good as a picture I can find. So Atsushi is from the RAC performance engineering team. So essentially, what is the performance engineering team? So at least I think this is the first time we are actually having Atsushi's team involved in such kind of presentation. So I want to spend a couple of minutes on what are these people doing. So these are elite engineers, so it's not easy to join the team. Believe me, trust me, I've tried earlier in the past. But these are the people who actually, instrument and measure code changes between, CPU usage, memory usage. They try to make sure that things are how it is supposed to be before it comes to you. So pretty much Atsushi and his team runs a lot of these tests, automated tests, and other things to make sure that we are not digressing from the performance improvements that we have introduced in the feature. They also provide a lot of feedback to developers about some new capabilities in the operating systems. We're using threads versus processes, real-time processes versus other things. So there are a lot of these things that go into as feedback. And this is both on generic systems and Exadata. And also, as they are doing this performance things, they try to increase the diagnosability by adding, say, additional statistics to AWR, so that when a customer case comes in, we are able to quickly diagnose those issues. So in short, that is a very, what you say, small introduction about the hundreds and thousands of things that guys do. I think already Sai mentioned it, but please use Q&A. The advantage of Q&A is that we can save this out and we can share it so that it is searchable on even when you ask a certain kind of question. So please do use Q&A. As I said again, there are Oracle RAC 19C. We always have been introducing it as a new generation Oracle RAC. Why is it a new generation? What is different from the older part is that we always knew RAC can scale most of the typical traditional applications. So what are the traditional applications? Traditional applications are applications which have been around for a while. They have been planned, and all this architecture of the application, the database schema, and everything has been thought through. So we always had this traditional application scalability features. Now what we are saying is you can also see this new kind of applications which are typically using JSON, and the schema changes pretty much very often, and all those other kind of newer application using IoTs and all that. So we are saying that we can even scale these new kind of application. So yes, I did mention this about SAP. You have seen this graph many times where we are able to scale from 2 nodes to 4 nodes, easily, meaning from 15,000 to 30,000. But did you know that we can also scale our IoT-based workloads? So this is actually a very old, I think about 4 years old, benchmark where we are able to scale, IoT workloads. So you can see that using different kinds of array inserts, you're able to get much improved numbers. So you can see you're able to get 200 million rows inserted per second. This is phenomenal numbers. But if you look at it, where's RAC in that? Well, actually, these numbers that you see are achieved by running this workload on Oracle RAC clusters. So if you see when you're running with an array of 5,000, we're able to achieve over 8-node RAC, basically 200,000, 200 million, IoT inserts per second. So this is amazing numbers. These are very great numbers. So mainly what we're trying to say is what happens below the covers. How did we reach this? How did we achieve this? That's what we're going to cover today. whenever you're talking about Oracle RAC performance, and I've dealt with it for the longest time because about 20 years ago, I was sitting as a support engineer where you guys will report to me problems about RAC, and I would say most of my experience, the RAC performance was more about network latency. So there is this concept called as a private network, and a private network essentially is a way by which Oracle RAC synchronizes its changes in memory. Because remember, you're doing insert, update, deletes in from different nodes, and we need to sync up. And this is the method to synchronize. In the cloud world, private and public network seems to be a little bit diluted. So let's make sure we define what is a private network. So private network is to be translated as a requirement to have a distinct, isolated, low latency network, simply put. Okay, so what that means is the private network should not be shared with other things. So example, I've seen a lot of issues where customers say, oh, I only back up at the night when there's no transactions going on, and therefore I will put my backup network along with private network. Really bad idea, don't do it. It's also very important for security, because remember that when you're using the private network, and Oracle RAC Cache Fusion is sending and receiving data over the private network, this is supposed to be isolated from outside the cluster node. So this is something that you need to think about when you're talking about security. We also utilize UDP on generic systems. Again, we're talking a little bit more about generic systems now, so we're talking about UDP, and we have our own error correction mechanism and all that. We do support redundant network. So there, if you have like some NIC bonding or whatever you might have, or teaming as they call it in certain operating system, is supported. We also have our own called HAIP, which seems to have been very widely used, and we have seen very less issues in terms of how the Oracle RAC cache vision behaves when certain errors are introduced or certain issues occur in the redundant network defined. This question comes up all the time. Yes, we do support network virtualization using VLANs, especially in those hyper-converged infrastructure. So yes, we do that. My only recommendation is make sure that the adequate quality of service settings are set up for the private network. So if those private virtual networks are getting inundated, it will still try to give more of its bandwidth for private network, which is very essential. So why did we use UDP versus TCP? So TCP is very well known. It is basically when you send a message, you get an acknowledgement. So there is no need for the sender and receiver to sync up outside of this. All the messages that we send are received or acknowledged. It has inbuilt support for retransmission, flow control, and also it provides what we call as ordered transmission, which means that if there are multiple messages being sent, there is an order established by the protocol. UDP, on the other hand, is a bit of a stateless protocol. So you'll have messages coming sometimes asynchronously to each other, saying, there are messages. There is no flow control, and there is, no order. So all of these things are something that Oracle RAC has added on top of UDP. Now, if you think about why not just use TCP? Well, numbers show that UDP is a little bit more efficient protocol in the workload that is that typically is prevalent in an Oracle RAC database. So again, it's not against TCP, it's not against for anything else. It's just a way that UDP provides better numbers, very low overhead on resources. Additionally, this may change in the future, depending on the newer technologies coming up. I'm not at liberty to discuss this right now, but hopefully once this happens, we will share a bit more information on that. So what did we do to improve Oracle UDP? So basically, we have our own state sequence control on top of UDP. So we have our own message things. So what we do is when the process sends and receives messages, we kind of have an internal acknowledgement sent on our own. And we have this special thing called, if we don't get an acknowledgement, we send a side channel message. Now, what is a side channel message? A side channel message is a very, very small message. Think about it this way. When you're sending UDP, you're sending typically in what database blocks size. So let's say you're sending an 8K block, and don't worry about whether the UDP itself will fragment it for now. Let's not worry about it. But the point is, if an 8K block doesn't get received on some time, and we send a side channel message which gets received, or which we get an acknowledgement for, then we kind of define this thing as a lost block, and then we retry sending the message. This is a bit expensive operation, because whenever you send and receive again and again, you have to remember that the process that is sending is kind of stuck, and it cannot do some other things, or cannot process other messages in its queue. So this is a bit important for you to understand. And lost blocks can be caused by, like, say, flaky private network. When I say flaky, it means it works most of the time, but there is once in a while it doesn't work. And high CPU saturation, what we call that, is basically network is good, the message is delivered, but there is no CPU on the receiver side to actually go and receive that message. So it's kind of like the message is not going to be received, which means it's going to be defined as lost. Make sure that you configure your private network. So the installer gives you a lot of choices. So in this case, as I've shown, the installer asks you that this is a public network. You can choose ASM and private together. It's fine to combine ASM and private network together. I did say they have to be separate, but ASM utilization of the network is so small that it doesn't affect the private network usage. The second thing is, if you're going to do it post install, then basically you're going to see that a lot of this OIF commands to add these things, and you can see how they are supposed to be looking when you say OIF get IF. If you really want to know a little bit more, especially when you add more private networks, we utilize something called Oracle HAIP. So if you want to know how it works, how we detect errors, check out that slide share link that I put there. I go over how does Oracle RAC manage resources that I presented at UKOG last year. Again, like I said, there's a Twitter handle. If you have questions, feel free to reach out to me. Um, Obviously, once you have chosen the right one, you want to make sure that your correct private network is used. So make sure you see this error, messages in the alert log. So it'll tell you this is IPC lightweight over UDP. That means everything is good. You look at the IP address. The IP address, if it is 169.254 range, we are using HIP. So this is good. Exadata, I just pointed out, is a little bit different. We use RDS IP, so you would see the difference. Also, if you want to check in your, let's say you're looking at a performance report and you look at your AWR or ADDM, you would see similar entries. So in the cluster, on the generic system, you would see this 169.254 address. On Exadata, you see this 192.168 address. We do not use HIP on Exadata. So if you see in HAIP on Exadata, that typically means it's a misconfiguration. Something has changed and you need to fix that. So how do you know you have some blocks lost? So this is a typical entry I've seen. So if you see this blocks lost, you would see that there is a section in an AWR or ADDM report that you would see where we define and show blocks lost. So in this case, I've highlighted there's those 348 lost blocks. The key to understanding lost blocks and how to debug that is to see it's not the absolute number that matters. What matters is the rate of increase. So if you have, let's say, certain, let's say 348 lost blocks and it's static over a period of time, then maybe it's fine. It's just the way that your network is, or if you really think that your network is perfect, then we need to go, and I'll give you some ways on which how you can debug this your network. Also remember that in this case, at least, they're only reporting lost blocks on instance 2. So if the network is the problem, typically, you would see some numbers on both sides. So the hint that we get from here, again, it's not an absolute thing, but it's a hint, is that, hey, maybe the guy who's reporting it is the one trying to send so many messages to the other side, and maybe the other side is not able to get it, maybe because of CPU or lack of CPU. Just again, a hint. While we talk about UDP, one of the things you have to remember is that even though we have these guys next to each other, sending and receiving blocks, over the network has a little bit more overhead. So for example, this is a small entry here which shows the path that we have to go through. So if you can see that this is a sys a user mode, it has to go to call it IPC, then there is a context switch, goes to the driver stack and to the network and the wire, and it goes back all the way to the other side. So there are a lot of these things that are going on in terms of sending and receiving blocks. So therefore, having lost blocks, is something that you need to investigate. I have a small cheat sheet of things here. So obviously, if you're using OS Watcher or something like that, you want to make sure that you look at some of the netstat output. So you can see that if you see a UDP overflows or packet receive errors or fragments dropped, you want to check for maybe it's a UDP send receive buffers are not correctly configured. You also want to check for high CPU utilization caused by packet fragmentation. So there are this netstat minus S IP, excuse me, IP stat numbers where you see this reassembled failed. That typically means there is some kind of issue that is causing this packet assemblies to be failing. Sometimes it could be as bad as the checksums failing, which is a really bad issue because checksum failing means a packet that originated at a certain site, when we reassembled it on the other side, it's not an exact copy of the packet that come in. That's actually also a security issue. So you want to maybe look at it with a little bit more due diligence. Again, these are all common errors. One of the other things is mismatch MTU. We keep talking about jumbo frames. Jumbo frames is recommended. I think in the, at least in 2020, we have seen very less infrastructure, if any, which doesn't support jumbo frames, but some customers are still utilizing, 8, 10-year-old switches sometimes, and that may not support jumbo frames. So you make sure everything in the stack is having, correct MTU. Having said that, there are a lot more information about this in this note, Moss note. I think I wrote it something like 15 years ago. It still is valid. We keep it updated. So it goes through all the issues that are possible step by step. So definitely look at it. It will give you some more ideas. So you'd say, Anil, there are so many things you asked us to check. Isn't it easier for Oracle to check for us? Well, thank you. We have had these checks in OraCheck. So if you see, we do check these things. So it says here in the check that is passing that maximum memory used to reassemble is configured at recommended value. So we do check some of these things for you. But at the same time, there are new checks coming out and, there are new things happening. So definitely go through that note. It'll provide you more information. Finally, I want to talk about something like, hey, how do I make sure my private network is actually performing at the best? I think, Anil, you describe your private network requirement as, low latency. So one of the things that you can use, and again, iPerf is not an Oracle tool. It is, available for anybody. It's a freeware, I think. But go and download and look at it. And you would see if you run it, you basically should be able to get good numbers without a lot of packet loss. Now, upfront, I'll tell you, there may be some packet loss depending on some of the parameters that you use here. So it is possible for iPerf will be sending, or you can configure iPerf to send in a tight loop, lot of information to the server side, and therefore make it run out of CPU and have some kind of blocks lost reported. It's fine. You got to just make sure this is one of the things that we used internally. So you can try with these, and you can tune up and down based on your network and infrastructure. Hopefully that gives you a very good high-level understanding of what to check and what are the most common network related or private network related problems that could affect Oracle RAC performance. Without any further ado, let me give it to Atsushi, who's our performance engineer. Atsushi, if you're ready, I'm just going to stop share and then you can start. Is that good?
Sure. Okay, let me start sharing.
Okay. So I stop sharing, and I also look at the questions. Do not worry, I will answer the questions, and if there is a thing that is overflowing, we'll get to you. I'll share and make sure you guys get your responses. Go ahead, Atsushi.
Hi. So can you hear me and can you see my screen?
I don't think we can see your screen. Can you?
Yeah, we can see.
Yes, we can see it. Yeah, it was just hidden. Sorry.
All right, so let's get going. So thank you again. So my name is Atsushi Morimura. I'm one of the RAC sort of say performance specialists here at the Oracle RAC development group. So before we start, let me just briefly introduce like who I am. I started my career with Oracle way back in 2001. And I started this in, I was doing this in APAC in Japan. And I started off as a sales engineer. And 2001 was a very important year for us because this is the year when Oracle released the 9i version of the software. And the marquee feature, the most important feature for Oracle 9i was actually real application clusters. So, as a new sales engineer, my job was to learn how this new technology called RAC works, work with customers so that to make sure that everybody can successfully deploy this new technology that Oracle just came out with. 5 years after, I got an opportunity to transfer to development. So I relocated to California, and 14 years since then, somehow I'm still doing cache fusion performance analysis work. So yeah, I've been doing RAC performance basically for 19 years now. And a key component of my work today, like Anil said, we do a lot of benchmarks, we do a lot of performance projects for upcoming releases. But another important thing that we do is we work with customers like yourselves, right? We look at performance problems that are reported to us from you guys. We look at if you're comparing say 11G and 19, and if you see good performance with 19, we work with you to understand what has improved and what else we can do to make your life easier. Okay, so yeah, all in all, I'm just really grateful to have this opportunity to talk to you guys because this is how by talking to you guys, this is how we get an opportunity to improve our software further. Okay, so today what I'm going to talk about is it's going to be the first half of my talk. We'll try to cover some tips and tricks that you can use to basically understand your RAC AWR reports better. Okay, and a lot of you probably have seen when you're looking at RAC AWR reports, you see these wait events that start with GC, right? Global cache. We at development, we try to make these wait events and statistics as intuitive as possible. But we also acknowledge that if you see busy, what the hell does that mean, right? We get a lot of questions from customers that you see this wait event, now what should I do? So hopefully through today's talk, we could get some clarity on some of these common questions that are reported from the field. The second half of the talk, I'll try to cover some new RAC performance optimizations that either we've implemented over the last few releases or we're planning to do in the upcoming releases. Okay, there's lots of work we did in the Exadata space because we have the advanced networking capabilities on Exadata. But it's not just Exadata. Even for non-Exadata platforms, we also did a lot of important optimizations. So hopefully, with all these new features and new technology that we're deploying, your life will be easier whether you use Exadata or not. Okay, so let's start with the performance troubleshooting tips. So like I said, the goal here is to help you understand your RAC AWRs better. And by that, what I mean is we want you to be able to understand what's going on. We want you to be able to root cause any performance you're seeing. And hopefully by root causing, you'll be able to solve some of the performance problems that you might see in your AWR reports. Okay, so before I get into that, here are just some common, messaging patterns that we see in RAC, okay? So there's this thing in RAC, there's this very important background process called the LMS process. I'm sure a lot of you have heard of or have seen this background process in action. But this is the very important process in RAC who is responsible for servicing all your cache fusion requests. Okay. In RAC, there's another very important concept called the distributed lock manager. We call it the DLM. Every resource in your cluster, for example, or your buffer cache blocks or your enqueues, these would all have a master instance, and the master is responsible for keeping track of the state of that resource in the cluster. So, if you want to read some block, and if you're not the master, you will need to message the remote LMS to see to make sure that nobody is in the middle of an update, to see if anybody has the latest copy of that block, so on and so forth. Okay, so these two concepts, the LMS and the distributed lock manager, are the two key components for RAC. With that said, a very common access pattern you see is a two-way block transfer. Let's say you're running your application foregrounds on instance 1. What happens here is the foreground will send a message to LMS through the private interconnect. LMS will then respond with a block transfer. So this is your most basic cache fusion flow. You send a request and you get a block back, and you can continue with your application. This will happen if instance 1 is the master, but he knows that the block is held somewhere else in the cluster. So you basically request the block from the holder. Okay. Another common pattern is a three-way transfer. The three-way transfer would happen in clusters with 3 or more nodes. You basically send a message to the master. The holder happens to be a third instance, and the holder will respond back with a block. So it's, the holder directly responds back to the foreground, like you see in the diagram here. So this happens when the master is remote and the holder is also another instance in the cluster. Okay. So these two patterns, the end result for these two patterns is that you get a block back. There's another pattern that you see in the right here is what we call the lock grant. So this happens, what happens here is the foreground sends a request to the LMS. The buffer is not held anywhere in the cluster. So LMS will respond telling the foreground, hey, I'm going to give you permission to read from disk. So go, here's your lock, just do your IO and complete the request. Okay. So, if you're in a freshly started instance, you're going to see a lot of grants. If you have a lot of IO, if your data set size is, larger than your buffer cache size, you may see a lot of these lock grant patterns. The good thing about RAC is no matter how big your cluster is, even if you run a 16 node cluster, like some customers do, we'll not see more than this three-way transfer pattern. Okay, that's because we can always get to the master in one hop, and the master knows who the holder is. So there's never a requirement to go 4 hops or 5 hops to complete a cache fusion request. Okay, so that's one of the architectural benefits of RAC. So going into the wait events, this is the most common wait event that you will see in the cluster. And there's some patterns here. So the wait event starts with GC, that's short for global cache. The next sort of section there would either say CR or current. This just tells you, the type of block that you got back in your cache fusion request, whether you got a consistent read block or a current block. The next one is what I just talked about, right? If you got a block back from the server, then the wait event will say block. If you got a lock grant, it will say grant instead. And the next section is what we call the performance hint. This will be either 2-way, 3-way, busy, or congested. So here we're going into, so there's more details about the performance hint in the next slide. 2-way and 3-way, these are pretty intuitive, right? 2-way means you went to LMS and LMS responded with a block or grant. Simple, right? 3-way is also simple. You went to the LMS, you went to the holder, and you got your block back. So these are what we call immediate requests. The only delay here is the processing delay and the network delay. But otherwise, there was no queuing. You didn't have to wait for anything to finish. You got your request back immediately. The tricky one is the busy wait, okay? Busy happens when LMS got the request, but LMS was unable to immediately service the request for a variety of reasons. The most common reason is, let's say, we are sharing a dirty buffer. Somebody updated the buffer, another instance wants to make more changes to that buffer, for example. When we share a dirty buffer in RAC, we must flush redo before we can share the buffer, okay? We do this to make sure that changes are recoverable when there's an instance crash, for example, or a process crash. So we must flush redo before sharing a data buffer, a dirty buffer. And while we're waiting for that flush to complete, we queue that request in LMS. And when this happens, you're going to see this busy hint, okay? There's other reasons where you might see busy, and that's the case when the buffer was pinned by somebody. What I mean by pin is, let's say you have some process who is in the middle of making some changes to a buffer. When that's happening, the buffer is pinned. And when the buffer is pinned, you must wait before servicing cache fusion requests, because someone is in the middle of changing that buffer. You want that change to complete before you can share it. Okay. So this is another case where we'll queue the request and mark the wait as busy. And there's a few other causes, things that can cause a busy wait. And usually, we try to make sure that you can explain these by looking at the AWR reports. So we'll have more details on that later. Okay. The last performance hint here is congested. A lot of customers sort of confuse this, that, oh, I see a lot of congested waits, I must have a network problem. There must be some congestion in my switch or whatnot, right? It's actually not true. When we see congested, this means that your LMSs were congested. The Oracle background process was very busy. It had to process a lot of requests. So we marked, the request was sitting in the LMS queue for a very long time before it was served. The request was, when we see congested, the request is actually processed immediately. That means without any of these, these queuing problems that you see in the busy scenario. But still, LMS was extremely busy and was not able to process it quickly enough. So, if that threshold, there's an internal threshold we use. If the request was sitting in the LMS queue for more than 1 millisecond, okay, see here, then we just, automatically mark the event as congested. So like I say here, this usually indicates that your LMSs are starved. And, a common remedy for this is, one thing you can do is to increase your number of LMSs so that there's more parallelism. There's less congestion in the LMS processes themselves. Or, sometimes there's things you can do in your application to remedy the situation as well. Okay. So here, I'm just explaining the wait events that I just talked about and what's the expected range and what causes problems for these, okay? So if you see a lot of GC current or CR or current two-way, three-way wait events, on a non-Exadata box, we should expect the wait times, the latency, to be usually less than 1 millisecond, okay? If you are on Exadata, this should be much faster. For example, a two-way wait event should be usually less than 100 microseconds, maybe faster if you're using the later, newer generation of Exadata. Okay, so if you see anything over this, that's a potential, red flag that something wrong might be going on. So, if you see bad latencies for the two-way or three-way wait events, the usual suspects are, your network might be congested. Your systems might be CPU saturated, either your client side or, either the requesting instance or the serving instance. If either one of those are saturated, then, your two-way, three-ways might be slower. The other, I wouldn't say typical, but it happens, thing is, So we run these LMS processes in real-time scheduling class. So if you're on Linux, there's a scheduling class called sched_rr. So we run LMSs in sched_rr and the equivalent, on other platforms to make sure that they're super responsive, even under high load. This gets configured automatically when you install Oracle. When you run root.sh in your database install, we change permissions for some bits in the Oracle home/bin directory so that we can elevate LMSs to real time. But if you have a configuration issue, let's say you have a 4-node cluster, you forgot to run root.sh on node 3, then this elevation of priority is not going to work, right? So if that happens, your LMSs will not run in real time, and you might see performance problems. And usually, Anil was talking about OraCheck. By running OraCheck or ExaCheck on Exadata, we'll be able to detect these problems pretty easily, so that you don't find them during your workload. Okay. Congested waits. Congested waits, it's pretty straightforward. So if you're on a healthy system, we should never see congested waits on a healthy system. So if congested waits, the moment you see them, that's a clear red flag that there's a performance issue going on in your cluster. Okay. And the reason that you might see congested waits is it's the same reasons as what I described in the 2-way, 3-way events. It's just that when you see congested, that's usually a sign of pretty extreme high load on your systems. So that's going to be the obvious thing to check. Okay. Now the block busy waits, these are a little bit more tricky. Like I said in the previous slide, the reason you see busy might be different depending on whether you had to flush redo or if if there was a pin held on that buffer. Usually the most common case is the redo. So one would expect the busy wait to be your immediate transfer times, your 2-way, 3-way transfer times, plus the log file parallel latency. Okay. And so therefore, if you see very bad latency for block busy, the most usual suspect is that you have some IO problem. Your redo flush is slow. Or if the cause is
Sushi, I think you're breaking up a bit. Can you double check? Oh. Sorry.
Is it better now?
Yes, it's better now.
Okay. Okay, hopefully my Wi-Fi, my network will stay alive. So yeah, if you see block busy waits, that's usually an indication of a hot block. If it's not log flushes, then your application, all your sessions in the application, they're trying to update the same block. Okay. And the other cause of, if you're seeing a lot of pins, then it could also be a high CPU type of problem. Okay, we'll have more examples on the block busy case later. But before I go there, there's another very common or important wait event with RAC, and that's called the GC buffer busy waits. This could either have a hint following the GC buffer busy, either acquire or release. And that just depends on, it's just the timing in which the wait occurred. So I don't think you need to fully understand acquire, what's different between acquire and release. What this means is it's a lot of people confuse this with the GC current block busy waits. It's actually not. It's GC buffer busy waits. Think of it like, at the airport. Let's say you're checking into a flight at the airport, right? And there's one counter stall open, and there's 100 people waiting to check in, right? The 100 people that are in the queue, they all want to access that counter, but they have to wait because there's a queue, right? So all these 100 sessions waiting, they're waiting for GC buffer busy. The guy at the head of the queue, and he's taking time completing his flight check-in. He's the bottleneck, right? You need to address either the time, the average time it takes to check in, or you need to open up more stalls in order to improve concurrency. So GC buffer busy in RAC, it's just telling you that, hey, all these other sessions want to access the same block. There must be some guy at the head of the queue, either trying to complete a cache fusion request. Usually what you see is, if you see GC buffer busy waits, the head of the queue is usually doing a GC current block busy wait, right? This means that, you're most likely waiting for redo flush to complete, or, you have some PIM problem. So that, if you see these waits, rather than sort of dwelling on, what's up with all these GC buffer busy waits, but the key is to, try to identify who's at the head of the queue. Okay, so yeah, that's the, so, and the more sessions you have, I've seen, customer AWRs where some people run, thousands of sessions on their system, right? So the more sessions you have, GC buffer busy waits might show up as 90% of your DB time or 98% of your DB time. And it seems like it's the biggest bottleneck, but you really need to look at the head of the queue, like I was saying. Okay. So here are some dependencies. Oh, sorry, before I go there. So here are some other wait events that are less common. So I'll just briefly talk about these. GCCR or current request. You'll see these waits when you're doing like ASH analysis, hang analyze, and things like that, but you never see these in AWR. And the reason is simple. When the request is in flight, in progress, we always use this GCCR current request wait event. Once the request is complete, we will fix this up. We will change the wait event to one of these. Okay. So if you see these events that I was talking about earlier, that means the request is complete. And that's what you see in your AWR reports. If you see these indicate that the wait is still in process. So yeah, if you're looking at ASH or $V views, this is what you're going to see. There's a new event starting in the 18C release for Exadata. We have this new access method called direct read. And this indicates we're doing RDMA for cache fusion. I have more details on RDMA later. And last but not least, there's also this this multi-block request. It's just a batch, it's like what you see with IOs. It's just a batch of cache fusion requests in one request. Okay, so here are some dependencies. Like I was saying, if you see a lot of GCCR or current block busy waits, you would usually see very long log file parallel writes to sort of correspond with that. Okay. The important trick here is when you see GC current block busy waits on, say, instance number 3, your slow redo writes are not on instance 3. Right? Instance 3 here is your requester. He got the block back from a remote instance. So you need to check the IO performance on one of the other instances in the cluster, right? So that's one that's one sort of mistake that some people make. You see GC buffer block busy waits. You need to look at the other instances. Like I was saying, if you see a bunch of GC buffer busy waits, the usual dependency is that there's an underlying GC current or CR block busy wait. Like I was saying, this is the head of the queue. And so it's important to understand what's going on there. And usually if you see GC current block busy waits, the usual case is that you have slow redo IO. Okay. And the GC current block busy waits, these can be the dependent wait event for some other things. For example, if you see row contention, if you see index contention, it's very common that the current block busy waits are at the bottom. And it's not easy to capture these in AWR, the dependencies. But if you look at things like ASH reports or even raw $V queries, we have information to tell you the blocking instance and the blocking session when you see these dependencies. So it's fairly easy to to look at those ASH snapshots and try to track down, who the root of the weights are in your system. And a lot of times it could be on another instance. Okay, so moving on. So, the previous slide, I talked about some weight event dependencies. Here, we're correlating weight events with some OS stats or some other Oracle stats that you can look at. Okay, so like I was saying, if you see high weights for a 2-way or 3-way, it's usually the case that your system is pretty loaded. So your run queue length might be high, your VM stat, MP stat, these things might show high CPU. And there may be, or there may be network issues, right? So these are some of the OS stats that will be useful to review if that's happening. If you see congested wait events, it's particularly important to check your LMS CPU utilization, because even if you're, if VMstat will report your system CPU utilization, but it could be the case that, your system is pretty idle, but these two cores where the LMSs are running, they might be 100% busy, causing congestion, okay? So it's important to look at, the individual core stats or the process stats to see how busy your LMSs are. And last but not least, if you see a lot of these block busy waits, the first thing to check will be IO, okay? Make sure that your redo flush, your IO stats and whatnot, make sure that these things are good. So next, I'm going to go into some more examples. So I have 3 slides showing, some snippets from AWR. The first one here is we have this. If you scroll down in a RAC AWR report, you'll see this section called RAC statistics. At the beginning, you're going to see this stat, and this will tell you how many LMSs you're running and how many real-time LMSs you're running. The very first thing you need to check is to make sure that the number of LMSs and the real-time LMSs are the same. We want to make sure that all of your LMSs are running in real time. And like I was explaining earlier, if you forget to run root.sh, or if there's some other, problem with the operating system or whatever, you might see 0 here, right? So that will be the first thing to check. If you see 0 there, then basically stop there and fix the problem, right? And for that, you can run oracheck or exacheck and see what's going on. So before trying to debug things further, that will be the first thing to check. The load profile is also pretty useful, especially if you're comparing, say, I don't know, like if you're comparing 11G versus 19, and hey, you're saying, hey, we have a slower rack performance in 19. Well, first thing to check is the load profile. Make sure that you're, if you're doing more messaging or more, so this is the number of messages per second. This is the number of block transfers per second. If you're doing more block transfers per second in 19, for example, then, there's something different in the 2 runs. It's not, it could be a SQL plan change. It could be a change. It could be a difference in the workload. So when you're making comparisons, it's very important to make sure that your load profile is comparable between the two comparisons. Okay, so the next section, this one pertains to the GC current block busy waits. Like I've been saying, the GC current block busy waits are usually due to flushes or pins. And this is the stat on the server side, on the LMS side. Okay, so this tells you how much of these cache fusion requests that ended up busy were due to flushes or pins. So here you see a lot more busy waits were due to flushes and fewer were due to pins. We also see the histogram. So if for all the flush waits, less than 100 microseconds, a quarter of the waits were less than 100 microseconds, and there were some slower ones. But there's nothing extreme, right? There's nothing extreme in like the 10-second or less than 1 second range. the biggest outliers you see are less than 100 milliseconds. So it's pretty good. The pins, there's fewer pins, but there's more outliers here. Okay. When the most common case we see is, if you have an IO problem, you'll see something here. Even if you see, I don't know, like 1%, 2% here, this is an IO that takes over a second, right? So that's a problem. So if you see something, towards the right of this histogram, whether it be the flushes or pins, that's another red flag to watch for. If you see long pins, that's a little bit more tricky. Usually it could be CPU problems, like your box is very busy. But it could also be bugs in Oracle. Like if Oracle, if some component in Oracle is not releasing a pin, we've seen that in the past. It's not very common, but it does happen. So if you see crazy outliers for the pins, I think the best thing to do is just contact support or talk to Anil or whatever. Talk to Oracle and try to see what's going on there. Okay. The flushes are more straightforward. And last but not least, there's a section in further down in the AWR reports that tell you that gives you a breakdown of all the other instances of the traffic pattern in the cluster. So the example here I have on the screen, you're looking at an AWR report from instance 1. This says that among all the CR blocks that we received, that instance 1 received, this much blocks were received from instance 2, and this much blocks were received from instance 3. The same thing with the current blocks. So you have a lot of current blocks coming from instance 2, fewer from instance 3. And among those, if you look at the data blocks received from instance 2, 82% of those were immediate, 2-way or 3-way. None of them were busy, and 17% were congested. You see less congestion for instance 3, right? So that gives you. It's interesting here because there's an imbalance here, right? You're receiving more data from instance 2, less data from instance 3, and that itself could be due to a config issues. Excuse me. So it could be either a config issue or a workload issue, right? If your workload is imbalanced, if you have some issue with your load balancer, for example, and if your workload is imbalanced in such a way that a lot of your sessions are running on instance 2 and fewer are running on instance 3, then if you're looking at instance 1, you might see a pattern like this. You have more activity coming from instance 3 and less from instance 3. So check for application imbalance, if that's the right word, if you see this type of behavior. Also, if you have if your configuration is imbalanced, let's say you have more LMSs on instance 3 versus more LMSs on instance 2 versus 3, then that could also lead to issues like this. We'll check for imbalance, whether it be config issues or workload type of issues. Okay, so that concludes the how to read AWR section. Anil, do we have any questions that we should answer here?
No, but I think we're a little bit closer to the end, so let's continue on. I'll answer at the end, or we can answer at the end if you have time.
Okay, sounds good. So next, we're going to switch gears and talk about something completely different. So here we're going to talk about some of the new features or performance optimizations that we've worked on over the last few releases. Okay, over the last few releases, and sort of into the future. So this slide sort of explains. It lists all the performance optimization we've worked on for runtime. Okay, and the ones you see in these little boxes, these ones are Exadata specific. The other ones, like you see here, are generic. They apply for both Exadata and non-Exadata. Okay. And just one thing, for the Exadata specific ones, we actually wrote a paper back in the spring this year So if you're interested in these Exadata specific optimizations, we have, you can look up this paper online and we'll have more details there. So in today's talk, I'm going to focus on these RDMA features first. So starting in 18C, we started to adopt RDMA technology for cache fusion. So we're going to talk about that first. So what is RDMA? RDMA is a networking technology where, let's say you're running some application on server 1. So you're running your application on the CPU here. The traditional model is if you want to access some data on the DRAM in the other host, the classic pattern will be that you will send a message, some background process or some daemon process on server 2 would receive that message, do some processing and respond over the network, right? That's the traditional network programming model. That's what we always do in cache fusion in RAC. RDMA is different. So RDMA does not involve CPU or the operating system on the other host. What we do is the network card can directly access the DRAM, the memory on the host. So let's say you're a foreground running on this instance. So you know the address of the of the piece of memory in the other SGA that you want to read. So what you'll do is you'll just send a message to the HCA. The HCA will directly look up that memory without waking up any process and will just respond. Okay, so it's done in the hardware. It doesn't involve operating system or CPU. So it gives you very low latency, and it gives you very low latency. And you might have seen from our colleagues that work in Exadata, so we started to adopt RDMA technology, especially in the latest X8M release. So we do RDMA for log writes, we do RDMA for buffer cache reads to give you very, you can do your buffer cache reads in around 10 microseconds now. And we see the same in RAC, right? It's not just the Exadata IOs, but we started to adopt the same technology for RAC. So like I was saying, the classic model was to always message LMS and get a response back. With RDMA, you remove LMS from the picture. It's a completely one-sided operation now. So if we do the math, if you're around 80% of the cache fusion round trip could be optimized or eliminated with the RDMA model. And we started to leverage this in some different, some specific types of cache fusion transfers. For example, the pilot sort of model we started to use was when we had to do undo block reads in RAC. This was the first use case where we started to use RDMA for cache fusion. And in the next release and the upcoming releases, we're expanding the scope of RDMA to other types of workloads. Okay, the biggest one here is what I highlighted in red. So starting in the next release, we're going to start to do RDMA for shared block reads. So all your regular tables and indexes, if we're doing shared read, a lot of these will be replaced with RDMA, which doesn't involve LMS for the most cases. I have more details in the next slide there, but the key thing is that the important thing to understand here is that we're actually not replacing all cache fusion with RDMA, because if you need to do a DML and you need to get an exclusive lock, we will still need to go to LMS. So that stuff is not going to change. But we're doing for the more simple use cases, we're trying to adopt this technology more and more, so that at least we're not going to eliminate all your LMS messaging, but hopefully there will be less, and that will by doing so there will be less performance problems that you'll see in your applications. So this is just an example of what will change with RDMA. So in the very simple case that you see in the left here, if If you're the master and you know there's a remote holder, you just do a direct read from the other instance. You don't have to message LMS. LMS doesn't have to do any work. You just directly read that piece of memory in the SGA. So that's the best case possible for RDMA. The other case here is, let's say you're not the master. So if you're not the master, you still have to send a request to LMS. The difference here is LMS, instead of taking the expensive path and sending back the 8K block, it will just send a lock grant. So you go to LMS, LMS will respond, hey, just here's the block is at this address, so just do an RDMA. So the work for LMS is much cheaper, and then the foreground will just do a simple RDMA read to the SGA. So if you compare these two cases, the overall latency will be pretty much the same because you still have to go to LMS. But the benefit here is that the processing in LMS is much less, right? You don't have to send a full Oracle data block. You just have to respond with a small message. So your overall LMS CPU will decrease, and hopefully that will lead to fewer, things like fewer congested waits and basically fewer problems, right? This pattern is more useful in clusters of 3 instances or more. So in the classic case, foreground will message LMS, then the message is forwarded to the holder and you get the data block back. What happens in this case is you'll still go to the master LMS. The master LMS will respond telling you, hey, that block is held on instance 3. Go read it yourself. So we have a regular 2-way round trip here, followed by an RDMA. So so the benefit obviously is that you don't invoke the LMS on the 3rd instance here. And we remove the messaging between LMS and LMS. So again, we not only we improve latency, but we eliminate a lot of the processing that had to be done in LMS. And here's an example from a case where we use RDMA. So in this case, the system is healthy. LMSs are not saturated. And you see your 2-way waits are about 100 microseconds, your 3-ways are about 180 microseconds. And that's within normal range for Exadata. And the key thing here is these RDMA reads, the GC current block direct reads, these are done in 8 microseconds, right? So you can see that the latency for RDMA is 15 times faster than your regular cache fusion waits. So that's pretty powerful technology there, right? But the bigger benefit is in the next slide. So here, what I did is in the lab, we just increased the load to a pretty crazy level. And, we artificially created the situation where, we see all these congested waits. So LMSs are completely bottlenecked. Their response times are 5 milliseconds, which is terrible, right? We should expect them in the 100 microsecond range, but now they're at, they're over a millisecond, and we see all these congested waits. Well, if you look at the RDMA reads, GC current block direct read, these are still completing in 15 microseconds, right? So since RDMA does not have a dependence on remote LMS, even if your LMSs are completely bottlenecked, your RDMA reads are not affected. Now you might wonder, why this was 8 microseconds in the previous slide and 15 microseconds in this slide. That's just because the host is busier, so your foregrounds are not getting scheduled quickly enough compared to the previous slide. But that's a client-side problem, and you're not seeing a server-side problem like you would see with the regular messaging patterns. Okay, so the point here is that RDMA is fast. That's a no-brainer. But not only is it fast, but it frees you from all these server-side issues that one would occasionally see with RAC, with all these congested waits. So it's a very powerful technology, and we hope, in development, we hope that we could expand the scope of RDMA to other use cases, not just shared logs, but potentially others in the future. And we hope that your applications will just basically run faster and will give you more deterministic performance under load when we use these new technologies. Okay. So next topic, so completely different topic now. We are well aware in development that there are certain types of workloads that that present us with some challenges with RAC. Right growing indexes, this is probably one of the most challenging workloads to scale well in RAC. So what we've done over the last decade or so is we took these workloads and we just we ran this day in and day out in the lab, and we just tried to look for ways to improve it. And here, what I have here is there's a bunch of code optimizations. These are not necessarily features, but there's a lot of things we improved in the code to make these workloads scale better. For example, the first one here, when you have a hot block, when you have a hot index, what happens a lot is the B tree will split very frequently because you keep inserting data into the rightmost leaf of a B tree. The index has to split because these leaf blocks become very full. They become full very quickly. Okay, and in 11G or the early the first release of 12C, we studied this split. We looked into the split operation, and we found a lot of cases where the split is not efficient, right? For example, the biggest problem we found is when somebody decides to start a split, he gets interrupted because some other process or some other instance wanted to read the branch block of that B tree. So you lose hold of your branch block, and the splitter has to go and re-request that branch block from another instance. And once he got a hold of it, some other guy, decides to request it, and it gets pinged away again. So this significantly slows down the split. And when you're doing a split, a lot of the others, all other sessions who want to access the same leaf block, they're waiting for the split to complete, right? So a lot of we did a lot of work to make sure that the splitter of a B tree index is not interrupted. When you start a split, we want to make sure that it completes without interruptions. So in 12C, we did a lot of work in that space. 18C, the sequence team, they added a new feature called scalable sequences. If your right growing index workload is using Oracle sequences, there's a new flavor of sequences, if that's the right word, called scalable sequences. What it does is it's simple. All it does is internally, the sequence numbers are prefixed with some instance specific value. So if you're on instance 1, you're getting a whole different range of sequences compared to your application running on this instance 2. And by doing so, you alleviate the right growing index contention because each instance will be accessing a different part of your B tree. Okay, so this is not if your workload, if your application is okay with having big gaps in sequence numbers being generated on each different instance, then this might be an interesting workload, interesting feature for you to try. One last thing I'm going to talk about here is there's some of you may heard of the Oracle sharding feature. There's been work done to leverage sort of some of the technologies that we have in sharding to RAC. So sharding is all about your application supplies a key, and there's this routing component to sharding, which will, based on that key that you feed it, it will tell you which shard to connect to, right? So that's what they do in sharding. And we just leverage that with RAC and use the same technology to determine which instance you're going to run on. So your database doesn't have to be sharded, but it's RAC. And we use that sharding API to basically do data-dependent routing or application partitioning. Okay, this will require some changes in your application, but if you already have a scheme where you do application partitioning, this might be something worth looking into to simplify that scheme using this new feature. Okay, so moving on to the last topic of the day, there's a lot of work. So when Oracle came out with the multi-tenant technology, multi-tenant came out in 12c. In the 18c release, what we did in RAC is to sort of align our the RAC locking scheme with the multi-tenant architecture. So we re-architected our locking to work better, to make sure that it works better with multi-tenant. So what we did is we now treat each PDB as if it's a different, as if it's an independent database within the cluster. By that, what I mean is it's probably easier in the example here. So let's say you have a 3-instance container database, instance 1, instance 2, and instance 3. And you have 3 pluggable databases, PDB1, PDB2, and PDB3. Let's say you only open your PDB1 on instance 1. PDB1 is closed on instances 2 and 3. In this case, all your lock masters, all your buffer masters, and all your NQ masters, they're all on instance 1. There's no mastership on instance 2 or 3, which means that if you run an application on PDB1, there's no GC waits, right? There's no cache fusion because all your masters are local. There's no need to do any messaging, and the buffers are never held on other instances too. So, it's like a single instance within RAC. We call this a singleton use case. And the good thing about this is if for some reason you decide to open the PDB on another instance, let's say you decide to open the orange PDB on instance 2, all you need to do is, auto pluggable database open, and it opens. And now you're, dynamically without having to stop instance 1 or PDB1 on instance 1, now you have a 2-node rack, and your mastership is distributed between these 2 instances. So, you can do these transitions seamlessly to scale out or scale in your PDB. So that's and in our autonomous database cloud, we find that a lot of customers like to deploy small databases, 2 OCPUs, 3 OCPUs, very small databases. If that's what you specify in our cloud, these singletons, this is what you're going to get. So a lot of, we see, our autonomous cloud databases, we see hundreds or thousands of these singleton databases, singleton pluggable databases in those systems. So it's a very common use case these days. In this example of PDB2, this one is open on all 3 instances. So it's essentially a 3-node rack. PDB3 is open on instance 2 and 3. So that's a 2-node rack. And of course, you can start a 4th container database instance, and you're free to open a PDB there if needed. So it gives you, the elasticity that, that are required in the cloud. Speaking of PDBs, there's this very important parameter called target PDBs. It's one of the new best practices for RAC for you to set this parameter. The value you need to set is, if you have, in this example, we're running 3 PDBs, right? PDB 1, 2, and 3. Just set this parameter, in this case, just set this parameter to 3, the number of PDBs that you run on the system. By doing so, we internally, we can size our lock tables and some other RAC structures correctly based on the number of PDBs that are in the system. If we don't do that, we'll assume that you're going to be running hundreds of PDBs on the system based on the number of CPUs on your box. And in that case, we might end up with undersized lock tables the lock tables might not be sized optimally, and you might have some performance issues. We're doing a lot of work to try to mitigate that problem. But in the meantime, for 19C or 18C, the best practice is to please just set this parameter to the number of PDBs that you're going to run. Okay, speaking a little bit more about this lock domain feature. So this also has benefits for failure isolation. So going back to the example of your orange PDB, who's a singleton, if for some reason instance 3, the CDB instance 3 decides to crash, there will be a little brownout for PDBs 2 and 3 because they're affected, right? The locks need to be reconfigured to compensate for the loss of that CDB instance. But guess what? If you're running, if you're just running PDB1, he can stay up and applications are not going to be affected. You can, applications just keep running without any freeze because PDB1 was not running on instance 3, so he's not affected. Same thing between PDBs. Let's say, you decide to open PDB3 on instance 1. So PDB3 becomes a 3-node cluster from a 2-node cluster. Activity on PDB3 will need to freeze a little bit because you need to remaster locks to between 3 instances. But whatever you're running in PDB instance 1 or 2, these are not affected because they're completely isolated lock domains. Okay, so some of you may be considering consolidation on RAC. A lot of customers are worried about isolation. By putting everything in the same instance, what happens if there's a failure in one PDB? What happens if there's a RAC instance failure? Well, the answer is, with lock domain isolation, you get pretty good isolation between PDBs, and for CDB failures, as long as you're not affected, as long as your PDB is not open there, you're not affected. So in addition to the performance optimizations that we can get from lock domains, we also have this component of failure isolation. And with that, that's the end of my. That's all I have for today. Any questions, Anil?
So I would say, Atsushi, we are very close to the end. So let's just I have one more slide end to cover just to close that out. And there's one question we'll see if we have time to address, but I did try to keep up on the questions. So if you could just unshare, please, so I can share. And there we go. All right. Okay, so thank you, Atsushi, for covering that in detail. I think everybody would, appreciates the practical tips and tricks on what to look for in a AWR report, because as obviously everybody knows, that's a lot of information there. Very good to focus on the key areas. Just to close it out, I would just want to reiterate that the new generation Oracle RAC performance features, again, we provide availability, scalability for traditional and the new application paradigms, complete single converged, and more importantly, secure database, while, as Atsushi mentioned, using the lock domain features, we ensure complete isolation between PDBs. Thank you again so much. I think I'll just take one question because I think Atsushi may want to answer that live. I'll read it out. So basically, there's a question which says, while LMS processing is reduced with RDMA, how is the resource locking mechanism handled? Who is responsible to update GRD? And Atsushi, let's try to keep that response within a minute, and then we can just call it a day. Go ahead.
Sorry, can you repeat the question again?
While LMS processing is reduced with RDMA, how is the resource locking mechanism handled? Who is responsible to update the GRD? Does RDMA itself manage the GRD?
Yeah, thanks. That's a very good question. So even with RDMA, we use the same mastership algorithms, if that's the right word. So the lock masters are the same, and we use the same methods to do that. With RDMA, what we do is, when we do an RDMA, we know who the holder is, right? If you're the master, that information is part of your GRD. So your lock table has information on who the holder is and what address that buffer is on the other instance. Right? So based on that information, we are able to do RDMA. The reason, so I mentioned that we only do RDMA in the next release for shared lock access. The reason for that is shared lock access does not require making any changes to the GRD, right? So if you need to do if you want to get an X lock, we need to change the state of the lock in the GRD. So that's why we need to make changes, and therefore in the next release we don't support exclusive locking with RDMA. We only do shared locking. So the short answer is, by doing so, we don't need to make any changes to the GRD structure. Does that answer the question?
Yes, I think that's good. Once again, Atsushi, thank you so much for coming on so early in the morning and providing us good introduction on how to read the AWR reports. What are the performance characteristics? I also want to take a second and thank AIUG folks. Again, you guys are wonderful. I really miss not coming over. Sai, you want to have any closing comments?
Yeah, anyway, we are top of the hour. Apologies, not allowing anyone to ask questions via voice. Awesome session, a very detailed session from Atsushi and Anil, as usual. Thanks for your support, continued support. Hopefully, we will see Atsushi's session, more sessions coming from you. And just again, it's very important, right? So please use a Twitter handle and hashtag, so you can thank. I don't know, actually, I'll follow up with Atsushi's Twitter handle, but please at least use Anil's and thank them via Twitter. And here is a speaker feedback. And if you want to ask any questions, that is also possible in this form. So please submit things. And the next slide, who's coming next week? So we have 2 sessions, by the way. So please mark your calendars. The first one is augmented analytics from Oracle Analytics team by Lucian. And also we have the security session as promised. We are going to run at least 1 session every month. So we have assessing your database security top 10 findings from Pedro. So please join without fail. With that, have a nice day, Anil and Atsushi, and have a nice evening for rest of the people joining from India and the rest of the world. Thank you for your time. Have a wonderful rest of the day. With that, we are closing this session. Thank you very much.
Thank you.
Thank you very much.